Hello everyone. In this video, we will continue our learning process with a capacity management technique that we'll study in chapter 7. So in this technique, I'm going to talk about a bottleneck operation. Number one, how we detect bottleneck. Number two, what kind of improvements that we can make to this bottleneck operation. And number three, what would be the potential improvement after we make that improvement? What would be the potential outcome or efficiency gain that we can see on the entire system? So let's get started with the question number 3 in the same practice set that I distributed. In this problem, we are given a manufacturing layout. In this layout, we do have 3 workstations. So station A here, station B is here, and station C is here. And in station A, we are given 2 different parallel identical machines. So in this machine, we can process a unit in every 12 minutes. So the processing throughput rate on station A is 12 minutes per unit. And again, machine 2 is identical to machine 1. It is again 12 minutes per unit. In station B, on the other hand, the production pace is 12 minutes per unit, and station C is 6 minutes per unit. And our first question here is part A. It says that which workstation among the 3 is the bottleneck workstation? Well, that's the first step to detect the bottleneck operation, is to understand the main flow of the entire manufacturing layout. So if you look at the first workstation, what we see here is that we do have 2 same machines. Assume that we do have a consistent flow, non-disrupted, coming into machine 1 and machine 2. And they are both working on these input flow independently. And as you can see, machine 1 can operate on 1 product, and it will be done in 12 minutes. And same for machine 2. Well, together, if we aggregate their capacity, workstation A should give us 6 minutes per unit, right? Because we can aggregate their production pace. And then if we do that, those are identical machines. Then we assume that the workstation A overall is giving us actually 1 unit in every 6 minutes. On the other hand, station B is going to give us 12, it's going to take 12 minutes to process 1 unit, and station C is going to take 6 minutes to process 1 unit. Okay, so which one is the bottleneck machine here? Well, let's convert these numbers. Let's say this is our A, right? Workstation A. We consolidated 2 machines, and we know that it is giving us 1 product in every 6 units, right? Say unit. Okay. And workstation B is 12 minutes per unit. Station C, 6 minutes per unit. Okay. Let's think in terms of an hour. All right, 1 hour. In 1 hour, how many units? In 1 hour, how many units I should expect to see coming after workstation A? Well, if you think about it, it takes workstation A to process 1 unit in every 6 minutes, right? How many minutes do we have in 1 hour? We do have 60 minutes. Well, if we wait for 1 hour, at the end of workstation A, we should expect to see 10 units, right? And if you do the same math in workstation B, if we wait for 1 hour, at the end of 1 hour, and at the end of workstation B, we should expect to see 5 units processed, right? And those are moved to workstation C, and workstation C's pace is 6 minutes per unit, and therefore, again, at the end of 1 hour, if there's enough supply coming into workstation C, we expect to see 10 units at the end of first hour. Well, what is the problem here? Well, although workstation A and workstation C, they do have the same pace, right? Working on a single unit in every 6 minutes, workstation B is only working on one product in every 12 minutes. So workstation B is definitely the bottleneck operation. So let's try to think about what the potential impact of this workstation B is in the entire production layout. Well, at the end of 1 hour after workstation A, we expect to see 10 units, right? But this workstation B is only capable of working on 5 units in 1 hour, right? And then workstation C is going to require 10 minutes so that it will be fully occupied in that 1 hour period. So after some time, let's say if you wait like after 8 hours, you would see accumulation of units here in front of station B. There will be excess inventory level because workstation A is going to work really, really hard, and workstation B is not going to be at that capacity to work out all the products that it has to that are coming out of workstation A. Therefore, you will have excess inventory that is going to be accumulating right before workstation B. And therefore, since workstation C is very fast compared to workstation B, it will be half busy, half occupied with the products that are coming from workstation B. And therefore, there will be no inventory here right before in workstation C. And sometimes people that work at this workstation will be busy, sometimes they will be idle. And this is bad, right? Some of your people are going to work hard in workstation C, and some of your people are going to be just staying idle in workstation C. Okay, so that's one of the problems that bottleneck operations create in our systems. Therefore, we have to balance the capacity accurately when it comes to dealing with this kind of operations. So let's continue solving this question. So in part B, it says that if the company operates 8 hours per day, 7 hours per week, what is the weekly capacity of this work cell? Well, first of all, since the bottleneck operation here is workstation B, let's think in terms of the entire operation, right? So let's think what's going on if we wait for 1 hour. At the end of 1 hour, how many products should I see here at the end of this framework? Well, the answer, we already gave this answer. That is exactly the unit that is going to be coming out of workstation B, right? And at the end of 1 hour, we expected to see just 1 unit of product coming out of workstation B, because workstation A is going to be working much faster. However, it doesn't matter because workstation B is going to slow the entire system down to reduce the capacity to 5 units. And workstation C, although it is faster than workstation B, it's only going to be processing whatever is coming from workstation B to C, right? Therefore, at the end of 1 hour, the capacity of this entire operation should be 5 units. Okay, so if our operation is just producing 5 units at the end of 1 hour, right? You can multiply this 8 hours per day and then 7 day per week to obtain 280 units per week. Okay, all right. In part C, the question is saying that if you could increase the capacity of any one of the 3 workstations, which one would you focus on? By how much would you increase the capacity of this workstation in units per hour? Well, Again, we already identified bottleneck operation, right? Station B is the bottleneck operation. The reason is that it is only delivering 5 units in 1 hour to workstation C. On the other hand, workstation A and workstation C are operating at the rate of producing 10 units per hour. The correct answer would be increasing the capacity of B to 6 minutes per unit, right? Or this is equivalent to 60 divided by 6, 10 units per hour. And by this way, we would align the entire system, so all of our workstations will be operating at the same pace. Okay. And then part D says that what will be the effective capacity of the total system after these improvements are made, referring to the previous part. It is basically saying that, okay, now in your workstation A, workstation B, and workstation C, let's assume that after 1 hour, you are producing 10 units, 10 units, and 10 units. Well, and at the end of the line, after 1 hour, it will be, again, 10 units per hour. Therefore, our capacity would be, updated capacity would be 10 units per hour times 8 hour per week times 7, well, this is hour per day. And 7 day per week. If you do this, it would be doubling our entire capacity. Well, long story short, by just improving, by just doubling the capacity of this bottleneck workstation B, we would be doubling the entire capacity of the entire system. That's something really, really cool. And in manufacturing or service environments, we look forward to making those kind of contributions to our overall system.